I got a bigger memory card, so hopefully, we can let the thing run through. Hopefully, the repository of videos online will help us out as far as revisiting ideas from class that you may not have picked up the first time. Looking back at last week, we on Wednesday. No, please don't apologize.
Allergies.
Yes, I know. Mine actually feel a little better today than they did last week. Anybody else had terrible ones last week? Are they getting better this week for anybody? No, not some. I'm sorry.
I live with the dog.
Are you allergic to your dog?
Well, my roommate's dog, yeah.
Your roommate, yeah. Yeah, I have 2 cats. I've had them for years and just recently found out that I'm allergic to both of them.
Yeah.
And I asked my vet, I'm like, when I was younger, my throat would close up, and right after this, my vet, I asked the allergist. My throat would close up, my eyes would swell shut, and now they don't. He's like, oh yeah, your body's just getting messed up in other ways. Awesome. So when I'm 60, I'll just have a great big delayed reaction of that. Yeah. So anyway, last week we kind of got through the intro to Prop Stat, and then I told you guys, bring any questions you guys have on that to class today, and here we are. So let's start the class. Any questions from that homework assignment, intro to Prop Stat? Anything give you guys grief? You want to chit-chat about, you want to check in with? This is how homework works. So we'll get as far as we need to get in class, as far as then assigning a homework assignment. Then we'll talk about it in class, and then we'll just keep moving forward. You keep the homework, and you'll turn in quizzes on that. That's what the quizzes are each week. So Wednesday, following Wednesday, Wednesday after that, and so forth. But the homework, as far as it goes, I'm often asked, do you do reviews before exams? I don't. This is your review. It's like an ongoing review, basically. So a few times a week, once or twice a week, we'll be going over these homework questions. So this is your exam review. I believe more in constant attention rather than big clumped attention right before an assessment. Because I think this is going to work, at least psychologically, I've been told this works better at creating long-term memory repository, if I used that word correctly. Did I? I don't know. We'll ask the YouTube folks. So any questions from Intro to Prop Stat? Elena, go!
So I would like to be sure, I want to be sure that I'm right about number 7, for example, and 8, page 17.
I want to hit a timeout real quick,
Okay.
and because of a word you used.
All right.
Elena used a very important word, and I want to make sure we make peace with that right now. She used the word, I want to make sure I'm right. There are certain computational things in this class where you're going to be on or off. It's black or white. Like, what is the average of these 5 numbers? There is one average. But there are some types of questions in this class that are going to have a spectrum of correct answers. For example, one of the last questions I gave on the out-of-class exam last term involved salmonella in my chickens. And I said, if I was going to test a large flock of chickens using combined testing, how much would it cost? And a bunch of students did it a bunch of different ways. All of the answers were correct, but they were different answers each way. So when you say checking that you're right, sometimes you might get frustrated at first if I say, yeah, I'll buy that. Well, yeah, but is it right? Well, I'll buy it. And you'll get used to that. You'll get used to the word ish. You'll get used to the gray between the ends of 1 and 0. So go ahead. I keep banging this
So
thing.
anyway, I want to clarify myself again. What is inferential and descriptive?
Oh, that's a great question. Who wants to answer that? What's the difference between descriptive stat and inferential stat? Who wants to take a stab? Please, and tell me your name again, my friend.
AJ.
AJ, go for it. Pick one of them.
Inferential stats make predictions based on random samples taken from a population.
That's awesome, AJ. So you draw a sample. You're interested in the population. For example, we're interested in how long it takes cold symptoms to go away in the general population. There's no way you can measure every single element of that population, plus their cold length of time. So you draw a random sample, and you extend that random sample's behavior out using, remember what you have to attach to whatever measure of your sample you draw to be safe, because oh good, there it was the margin of error. The margin of error has to be attached because your sample, if drawn properly, will hopefully be close to your population's value, but it won't be exactly your population's value. Go ahead, Elena, continue that question.
So the thing is, see, I understand that, and I read the book, and it's from the book, and
Okay.
I understand it, but in regards, for example, to number 7 and number 8.
Go ahead and read number 7 and number 8.
17. Determine which one of the following statements is descriptive in nature and which is inferential.
So which number is this, my friend?
So it's actually page 17, 1.7.
Page 17, 1.7. And one more slight apology for the textbook. Your textbook always puts a 1 or a 2 or a 3 dot hopefully you saw this on the homework sheet. The number is the one after, right? The
So-
1 is just a chapter. So 1.7, number 7, number
is
8.
the following.
Oh, number 8.
All 9-inch, largemouth bass, so bass
uh-huh.
in New York State are an average of years old.
Our average of 3 years old.
And B is of the largemouth bass used in the sample to make up to the NYSDEC, I don't know what it is, Freshwater Fishing Guide.
Okay.
Average age of 9-inch largemouth bass was 3 years. As far as I have understood, the first is inferential because it has got it's not descriptive, I think. I don't know. The second one for me, B, is descriptive because it describes and gives us more information, or what?
So I want to go back to
Okay.
a statement that Elena just said. When you draw a sample, read part B again, if you will.
Oh, B? Okay.
Yeah, just part B.
Of the largemouth bass used in the sample to make up the NYS DEC, Freshwater Fishing Guide, the average age of 9-inch largemouth bass was 3 years.
Awesome. So the assumption,
Sample,
the
yes.
assumption is that sample was a small subset drawn from all largemouth bass in New York State. Boom. And the reporting back said the average age was 3 years. Was there any margin of error given, plus or minus 6 months, plus or minus 3 months?
No.
Did they give it? They didn't go into that
No.
kind of detail. Totally fine. That is most definitely descriptive, isn't it? We drew a sample. We drew a sample, and this is the average age of that sample.
Yeah.
There's no question mark as far as, well, could we be wrong? Yes, we probably could be wrong if we're talking about the population, but it didn't say that. It said of the sample drawn, the average age is. So there isn't any prediction being made, is there? There's no prediction being made. It's
So
just,
it
here's a
is-
sample of bass. So I'm going to call that descriptive.
Yes, that's right.
Does that make sense?
Yes.
Did you hear what Elena said about part A? She called that inferential because the statement in part A was all the bass in New York State, I believe, all the largemouth bass.
All of them, yes. All 9-inch largemouth bass in New York State are of an average of 3 years old.
Now, there's no possible way of knowing that that's true or not. Because what would you have to do? You
test,
have
yeah.
to test every single bass. Tell me your name one more time. Thank you, Robin. That's right. Oh, wait. Right, but you're one of the awesome ones that transferred over from that. I'm envisioning you, Robin, in class at that side because for some reason that's how my memory works. Thank you. Just think of a bird.
Sorry, I didn't know it.
Just think of a bird. It's awesome. But it's got a Y in it, doesn't it?
It does.
I'm remembering that. Okay, good. Perfect. You'd have to, as Robin said, have to measure every single fish. Can't do that. So the statement that all bass all 9-inch largemouth bass in New York State have an average age of 3 years has to be inferential because it can't be descriptive. Does that make sense? Sherlock Holmes once said, once you remove the impossible, then whatever is left, no matter how improbable, must be the truth. That can't be a descriptive statement, can it? That can't be a descriptive statement because you'd have to measure every single fish. So therefore, it must be inferential. And it must be based off of part B, I'm assuming, because they drew a sample. That sample had an average age of 3 years. There is one thing I would love to see, though. I would love to see attached to that all largemouth bass have an average age of 3 years. And what is that? We mentioned it already today.
Margin of error.
I would really like to see a margin of error on that, wouldn't you? Because it's a ballsy statement, right? Can I say ballsy? I just did, I guess. It's a ballsy statement. It's a ballsy statement to say these bass average 3 years. Because they don't average 3 years. They average 3 years plus or minus something. I guess for you guys it's plus or minus or plus. So I'd like to see something like 3 years plus or minus, I don't know, a tenth of a year. So I'd like to see these bass average between 2.9 and 3.1 years of age. And the reason why would I like to see that? Why do I feel better about having that wiggle room? Who's got an idea of why a margin of error is important? Do you remember why we need to have that? It's okay if you don't. It's kind of early to have that be comfortable yet. Is that Jen?
Yeah.
Jennifer or Jen?
Either one.
Either one. Okay, go ahead, my friend.
So you can see which one's like really high or not, because if one's 3 and then the other's 4.
Love it. You can compare. So suppose, for example, I love that. That was perfectly said. Suppose you want to say, I want to compare largemouth bass from Connecticut, which are fed by the same waterways as the ones in New York. I think they touch each other from my East Coast days. And you want to see if largemouth bass there that are 9 inches long are the same age. Maybe they're older. Maybe for some reason their growth is slowed in Connecticut. The only way you're going to be able to tell if there's a difference is to attach a margin of error. So suppose the Connecticut fish have an average age of 3.2 years. and New York's is 3. Well, 3.2 is bigger than 3, but there has to be error in the measurement. And that's just because you're drawing a sample, you're not going to get the exact measurement that you're looking for. You're going to get most likely close to that exact measure. I say most likely. That's part of this class is identifying what that means. Most likely. How close? How close and how often are you that close? 2 questions we're going to answer for the next 9.5 weeks if you don't mind. But Jen, yeah, in order to do any kind of quantitative comparison, we have to have that wiggle room to see. And more of that to come very, 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 very quickly, actually, the next couple class periods. So yeah, I'd like to see it. It's not there. I'd love to see it, though. I'd love to see it. I mean, I think I mentioned the Gallup poll recently. Now the majority of people think going into Iraq was a bad idea. 53%, according to Gallup, 53%. Well, the margin of error on the poll was 4%, which means it might not be a majority. It might not. It could be as low as 49%. Once you attach that 4% to the 53, it might be as low as 49, which arguably is half. But not literally. It's not literally half yet. It's close. As a matter of fact, what's interesting, and we'll see this statistic, you saw it on Wednesday, that American flag graphic that Grand Reporter Jim had, that was 10 years ago when that poll was taken. And arguably then it was half and half. The red and the white in the American flag was half and half. So it's not much has changed. So finally a majority of Americans are opposed to Iraq. I don't think it's changed at all. I think it's still as divisive as ever. 10 years later. 10 years later. Cool? Does that make sense?
Yeah, but
go ahead, Elaine.
Number 8 is, I think, tricky one.
Oh, 8's tricky.
Yeah.
I like tricky.
So A, 84% of the teens in May and June of 2009 had cell phones.
Okay.
B, in May and June 2009, 16% of all the teens surveyed did not have a cell phone.
Okay.
So the only thing is that I paid attention to the word all teens.
Versus, and there was another word in part B that was not in part, go ahead.
Part A.
Somebody noticed a surveyed, right? There was a surveyed in part B. Survey implies what? Exactly, because it implies a sample drawn. Good. So if you hear survey, that means they asked a subset of the population, which means a sample was drawn, and that is definitely descriptive.
Yes,
that's Haley, right? Haley, yes. That definitely is descriptive because they said of the survey drawn, 16% had cell phones. 16? This was 2009. Older it is now. 61 probably. 85. It's something very much larger than 16. But yeah, that because you're reporting back from a survey, that statement is descriptive in nature. I would not be surprised, however, if Part A fed off of Part B. Here's the sample drawn, 16% of the sample. From that, we can conclude that 16% plus or minus, say, 3 or 4% now have cell phones. So you could, and again, go back to what Jen said. Maybe the claim was, because I used to teach high school, and people always used to complain about the kids having cell phones on them. Oh my God, every kid in the school has a cell phone. Well, according to that survey, if the kids in my school are distributed in the same way this survey was, no, that's not true. Because even if I put a 4% margin of error on that 16% survey, at most it's 20%, which is 1 in 5 kids, right? At most, it's 1 in 5 kids. At most, it's 1 in 5. So that's where you have to be careful with anecdotal evidence versus rigorous statistics. How many of you have sat in oh my God, it seems like there's 1 million hikers out here today when you're at a Broken Top or hiking up Green Lakes. You're trying to find your favorite little fishing hole. Oh my God, there's 8 million people down here today. Oh my God, everybody knows about this place now. I mean, those kinds of ridiculous generalities are so easy to default to. But if you take a step back and realize it, you could just be seeing an extraordinarily biased, extraordinarily outlier-laden experience compared to what's actually happening. Yeah, Lynn.
In the morning today, just on the radio, coming back to school today, I heard that it was said in an interesting way, because the guy said, well, it's already like this kind of flu, blah, 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 I don't remember which ones, but they've killed already half dozen people. Flu.
Okay.
It already. And then I started thinking, half dozen. You know, if he said just 6 people.
Sure.
Nobody would probably, but half dozen, how, the way he did it.
Yeah.
It's just like at least 500,000 people.
It's Katie Kirk and the 733.
It's amazing.
It all boils back down to that. Remember swine flu? H1N1, I think, which is the same thing, right? H1N1. Oh my God, did you all get inoculated for H1N1? You didn't. Okay, you didn't. But there was a panic. Did you hear the panic?
Yes.
It was going to kill everybody. What got washed under the rug is that more people died that year from the normal strain of flu than H1N1. But that's the one you heard about. It's the same thing that happens when a plane crashes. A plane crashes, everybody on board is killed. I'm not saying this is to make light of this, but that's what you hear about. What you don't hear about is that I believe, and now this is from a Michael Crichton book, so source this properly, more people are killed being kicked by horses every year than in aircraft accidents. But when a plane crashes, everybody dies and it makes the news. When somebody gets kicked by a horse in the world, you don't hear about it usually, right? I mean, people often ask me, if I'm scared riding my bike to work every day. Oh my God, you're out there exposed, blah, 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 blah. Now, again, on average, I think I do, well, I shouldn't say that because I never checked. The rate of the rate of accidents on bikes might be higher than the rate of accidents on cars. I highly doubt it, though. I highly doubt it. And I'm sure the death rate for bicyclists is lower than the death rate for cars. But even if it's not, it's an average. Even if it's not, it's an average. So when I hear that there's a 2% chance of death on a bike, I look at that and say, what does that mean? Out of every 100 times I get on my bike, does that mean I'm going to die twice? No, it means out of every 100 trips on record that have been shown, there have been 2 deaths per. This is very, very high, and much too high for what it actually is, I'm sure. I am just one data point in that average, and we'll see later on, especially with your guys' key data, how skewed averages can be. We'll get back to that. Cool? Anything else from there give you guys grief? Descriptives? Please, Jay, go ahead.
Well, on 15, I think it was.
15? Uh-huh.
Yeah. What does it mean by identify the statistics and give its value?
Okay.
Yes, that was good.
So you've got this block of text, I'm assuming, up above. Would you mind reading it to us?
Yeah. Of the adult U.S. population, 36% has an allergy. In a sample of 1,200 randomly selected adults, 33.2% had an allergy.
Okay, 36% have an allergy. Allergy.
Yeah, that was.
Okay. Then there was a sample drawn, Jen. I couldn't keep up with you very quick. How many drawn?
1,200.
1,200?
Yeah.
I'm assuming adults in the U.S. Randomly, good. And and 33.2% had an allergy. Okay. Was there a margin of error given?
No.
I love it. We're gonna add one in later. So, from those couple sentences, let's get the sample talked about first, because the population is a little bit trickier. Sample, 1,200 adults. Okay. Did they say randomly sampled? Mm-hmm. Okay. Let's trust them on that. Let's trust them on that. Okay. What's this right here? This 33.2.
How many of the adult population had allergies in the sample?
In the sample. So it's a measure of the sample, which makes it a what? Excellent. It's a measure of the sample, which makes it a statistic. 33.2% of the sample of 1,200 adults had allergies. Now up here, they're telling us that 36% of the U.S. population has allergies. Now, that's a pretty ballsy statement. Of every 100 adults in the U.S., 36 of those 100 have allergies. Ballsy statement or not, what is that? That's a value, a percentage of allergies where? In the entire adult U.S. population, which makes it what kind of a measure? This was a statistic. What's that?
Parameter.
That's the parameter, isn't it? Isn't that the parameter? Because that is the statement that says in the U.S. population, 36% of the entire U.S. population has allergies. Now, what did I just get done telling you last week about parameters? In order to know the parameter value, what do you have to do? You know that 36% of all adults in the U.S. have allergies. What's the only way? Think about what Robin said about 10 minutes ago. What's the only way to know that for a fact? Go survey. Basically do a census at this point, right? You have to do a census because you have to ask every single one. Did they? They most definitely didn't. What they did was they've got so many, tens if not hundreds of thousands of data points that they've concluded they've seen enough of the population to basically shrink the margin of error down to next to nothing. You'll learn in 244, and we'll start talking about it right now. With a sample of about this size, you have to accept about a 3% margin of error on this statistic. This is not exactly 33.2. I mean, excuse me, in the sample it's 33.2. But if you were to then say, ignoring that 36 for a second, if you were to say, okay, my sample, 33.2% had allergies. Roughly 1 in 3 of them had allergies. If you had to then report that to the news and say, okay, based on my sample, what percentage of the adults in the U.S. entirely have allergies? You shouldn't just say 33.2, because here's a question. Suppose you go back and randomly survey 1,200 people again. Are you going to get 33.2 again this time around? What are you going to get, do you think? Give me a possible value. 30?
Might be.
35? 35? What do you think? 36? But could get 36, yeah? What do you think? You think you're going to get 5%? Think you're going to get 86%? So chances are, whatever you do get, assuming this wasn't a goofy value itself, whatever you get the next time for 1,200 more people is going to be what? Close to 33.2, somewhere in that neighborhood. And because of that uncertainty, you have to put that margin of error on there to kind of make up for that. So let's suppose, let's go a little further than the problem. If you don't mind, Jen, a little further than the problem. Because this idea of a margin of error, how many of you guys are taking 244? You see, very, very few of you. The idea of a margin of error, some of you might need it, not realize you need it yet. The idea of a margin of error is tantamount in Math 244, which is the second part of the stat class. But for those of you not taking 244, to let you get out of this class without ever talking about it is a crime. So let's just assume that there's a plus or minus 3% margin of error on that sample statistic. And that's a function of two things. It's a function of the sample size, and it's also a function of what's called confidence. Very often, you guys will see this, when you read like a Gallup poll or Quinnipiac poll or some medical journal poll, they'll talk about 95% confidence. Remember how I mentioned, unless this number is really, really off due to randomness, that happens with 95% confidence roughly 1 in 20 times. So if you do this survey 20 times, 19 of those 20, you're going to get that on average over time. 19 of the 20 times, you're going to get numbers that are close to this 33.2. And the other 1 in 20 times, you're going to get what's called an outlier, a goofy one that's either too high or too low. More on this in 244, and also more on this as we go through the class, scattered throughout this class as well. Okay, so knowing that there's a 3% margin of error, you're not going to tell the press that 33.2% of people have allergies. You're going to tell them at least 30.2%, right? At least 30.2%, and at most, 36.2% have allergies. And you'll probably preface that or suffix that with, and I'm 95% confident, but don't worry about that. We'll talk about that more in 244. So here's a question. 33.2% is different than 36, isn't it? Which I've now erased over from my hand. 33.2 is less than 36. So the news will often say, oh my goodness, this sample, the people in this town, they only have a 33.2% allergy rate. What are they doing? What are they eating? What are they drinking? Is it local honey? Have they cut dairy? Do they sleep upside down to drink? But then you look at this and you ask yourselves, have they indeed decreased the allergy rate from 36%? And you have to say, not likely, because why? Because why? Say that again. I heard.
The 3% margin of error.
The 3% margin. Tell me your name one more time, my friend.
Armando.
Armando, yes. What number is between 30.2 and 36.2? 36. Well, 33.2 for sure. But if they're trying to claim that 33.2 is lower than 36, you say, not with the margin of error, it's not. The margin of error says that 36 is within the range of accepted values, which means you can't prove that it's dropped. If that margin of error were 1%, then we'd be talking, wouldn't we? Because then it'd be at least 32.3, but at most 34.3. And if at most 34.3, that is lower than 36%. Then we can talk. Then you have to talk about if that's worth bragging about. If you're down by 1.7%. If that's worth, it might be. It might be. That becomes practical versus statistical significance. And more on that in 244 as well. More on this too. Some of you are looking a little bit concerned about, wait a minute, I'm not quite buying this whole range. That's part of that is because the idea of variation within a sample is not the easiest thing to comprehend. And we got a whole section to kind of devote it to that. I want to focus mostly on the centers for today and probably into Wednesday, and we'll start focusing on the variation on Wednesday, and then tie it all together, and this margin of error will come back. But just for right now, realize, without a margin of error, it's very, very hard to believe much of what you hear in the news. It's very, very hard. I remember years ago, this is about 5 years ago now, they were talking about the Bend Lapine School District AP pass rates for AP exams. They said the national average was 59%, and Bend's clocked in at like 56.2% or something like that. And they were woeing, oh my goodness, Bend is below the national average. Maybe, but without a margin of error on that 56.2, I have no idea if it actually is or not, right? If it's 56.2 plus or minus 4%, I can't prove that it's below 59, because 56.2 plus 4 is 60.2. Which is actually above 59%, which might mean that Ben Lapine is doing better than the national average. You see what I'm getting at there?
And again, this national thing.
Yes.
So
where did that number come from?
Yeah.
Yes. Very good. Where does 36 come from? Elena's got a very good point. Very rarely are you actually going to get a true parameter value. Here's something, a preview of 244. If those of you not taking 244, keep this in the back of your mind. We'll revisit it towards the end of class. This margin of error, as sample sizes go up, what do you think happens to margins of error? They actually go down. Because there's less, right, because you're getting more people. So think of it two ways. Number one, if you're sampling more people from the population, you're getting more and more of that population, so you're less uncertain of the value you're getting back. I mean, essentially, if your sample size goes to infinity, there isn't going to be a margin of error at all, because you would have asked everyone. We would have caught every bass out of all those damn ponds in New York and measured every single one of them, and they're all 3 years old on average. But that's ridiculous, because you can't measure them all. But as this goes up, that goes down. And there's a mathematical reason for that, which we'll study towards the end of this class and all about it in 244. So the reason why they can claim 36% is this 36% essentially has such a small margin of error, it's not worth talking about. It might be 36% plus or minus 0.1%, or 36% plus or minus 0.05% at that point. So at which pace you just drop that and say it's essentially zero. This happens all the time. Have you ever taken your children to the pediatrician? They give you a growth chart. We're going to analyze this later on in this class, talking about my son and his growth charts. They show you the average age, the average weight, the median head girth, my favorite measurement. And they tell you it's this for this kid at this age. But it's not that. It's this plus or minus, but they've measured so many kids at that age that they can basically say the margin of error has shrunken down to zero, and we can just say the middle of that at that point. Is that fair? But fairish? Fairish. But at this point in time, when you see a sample of 1,200, 1,500, 2,000 people, demand to see the margin of error too, to see if the claim that's being claimed actually has any merit to be talking about. AJ, go.
So would the variable be, it says describe the variable.
What are we interested in?
The population, or the percentage?
What in particular? What is that percentage measuring? What? Allergies. We're interested in whether someone has allergies or not. So the variable of interest, I love the fact that AJ is asking this, and because of this question, I've learned to talk about variables more once we get going in the class, i.e. today. It's what we're interested in the study that we're studying. In this case, it's binomial. Here's a person in the sample. Boom. Do they have allergies? There's two possible responses to that, correct? Once you've defined what allergy is, who would rate themselves as having severe allergies? Yeah, me too. How about mild? Yeah. How about moderate? You see, maybe we're making this too simple. Maybe we're saying this too simple, but have allergies. I mean, should we break it down by mild to moderate, moderate to extreme? Not at all. Maybe we should make it more than just two outcomes. But that's not what I'm seeing here. What I'm seeing here is you either have it or you don't. So it's a binomial thing. That's the variable we're interested in. Do they have allergies or not? Cool? And percentages, which account for most of what you're going to see in the news, are usually binomial. Is Congress doing a good job or not? I was recently told, that was about 3 months ago, I saw a survey that Congress is now, what was it, Dakota? Congress is now less popular than herpes. The herpes infection rate is higher than the approval rate of Congress. It was something like herpes is 1 in 10 and Congress is 9 in 100 as far as the approval rate goes. Love that. But it's binomial. Either you have it or you don't. Either you approve them or you don't. It becomes binomial essentially, which means 2 outcomes. Cool? Yeah, good.
Just
To tie off of that, yeah.
Yes, exactly. So we don't have a word to identify the type of variable. It can be, for example, in this case, very dangerous, dangerous, somewhat dangerous, not dangerous. That's the type.
That would be qualitative, wouldn't it? Because unless you're talking, what exactly are you talking about there?
22, yes. It's page 19, it's 22.
Uh-huh.
So first is name the variable of interest, and second one, identify the type of variable.
Okay, gotcha. So what is the study of interest here?
A nationwide poll of adults on cell phone use and driving was conducted during May 2009 by the Harris poll. Their responses to how dangerous is it for a driver to use a cell phone while driving were categorized as very dangerous, dangerous, somewhat dangerous, slightly dangerous, or not dangerous at all.
Got it.
We spoke about it.
We did.
Time. Yes.
That's Likert scale data.
So the name the variable of interest.
The variable of interest is
the use of phones while driving.
Well, actually, not so much the use of phones while driving, but if it's dangerous, how dangerous that is. Because we asked a number of people, I've forgotten how many people we've asked now. We've asked them, how dangerous do you think it is to use a cell phone while driving? And their responses are basically the values of that variable. And there are 5 values that they're allowed to use, I'm assuming.
Yes, exactly.
Everywhere from not dangerous at all to extremely dangerous and everything in between.
These will be the type of variables?
I would call that qualitative. They're not numerical, right? They're not numerical.
Yes.
I mean, now I guarantee that numbers were assigned to those. I guarantee that completely safe was given a 1, and completely dangerous was given a 5, and neutral was given a 3, and at the end of the day they averaged those values together and said, oh, the average is 2.6, which means I don't know what that means. I don't know. I have no idea what that means. That's the problem with it. What I would say, I just saw this on my class evals. I went through my class evals for last term in 244. Likert scale data. Scale of 1 to 5. Literally a scale of 1 to 5. Strongly disagree, all up to strongly agree. In 1 or 2 of my categories, it was something like 38 5s, 7 4s, no 3s, no 2s, and 3 1s. And my overall average came back at like 4.1. But my median and my mode, all of which we'll talk more in depth about today, were 5. And the reason for that lower average was because those 3 1s were yarding the average down towards those 1s. As if the number 4.1 that makes any sense anyway. What does 4.1 mean when you have 5 values of the variable? You've got 5 values. You've got agree, strongly disagree, strongly agree, disagree, or neutral. 4.1 means nothing. There's no 0.1 between 4 and 5. You have 5 values to pick from. Which one did the best job of speaking to that? The one I got the most in. Just like this one, the one that came back the most in this one. The one that came back. And I love that poll too. Use of a cell phone while driving. Not talking on it while holding it, but use of a cell phone while driving. And I think there's a vast difference depending on that. Well, maybe there isn't a vast difference depending on that. I thought about this, being a bike commuter, I thought about this a lot. The whole idea of having a cell phone active in somebody's hand or actively having a discussion while somebody's driving. And the hands-free issue always comes up. Well, it's hands-free, but it's not brain-free. That's my problem, is that your brain is still actively, hopefully, talking to the person on the phone. So if your brain is actively doing that, it can't possibly, well, I'm speaking in terms of myself, who can't multitask. So, a very interesting research article there. Haley, what's on your mind? You look concerned about something.
I don't know. I'm just listening.
Oh, just processing it all. Okay, good for you. Good for you. Like, that question was coming.
Well,
Tell me
I
your
do,
name.
but
Oh, okay.
you can just keep going.
Okay, Rachel, go.
All right, so I was a little puzzled by number 16. It says, in your own words, explain why the parameter is fixed and the statistic varies.
We actually discussed that already, believe it or not. We did. Let's go back to this one to talk about it. Okay, 36%. Let's pretend that 36% of the adult U.S. population actually does have allergies. That's fixed, because the only way we're going to know that is because we checked every single one. And let's make it simple for ourselves. Let's say there's 100 million, forget that. Out of every 100 adults in the U.S., 36 of them have allergies. Why is the sample not fixed? Go ahead. This is Gen 2, right?
Yes.
Yes, go ahead.
Well, because the group of people surveyed changes.
Right. Every time you sample, say, 1,200 and more, you're not going to get exactly 33.2. It might be 31. It might be 36. It might be one of those goofy ones that's 96 or 1/2%. But because the subset you're drawing from is changing each time, that has to change as well.
Got it.
And what takes care of that? What takes care of that uncertainty? What magical little...
Margin of error.
This guy right here. This guy takes care of that uncertainty. Hopefully gobbling up 95% of the uncertainty. Does that make sense? Good. Very good question. Very good question. The parameter is fixed. Unfortunately, it's also unknown. That's the other problem. Yeah, it's fixed, but you don't know what it is. The best you get is this 30.2 to 36.2. Go ahead, Haley.
Okay, so for 23,
23.
it says students are being surveyed about the weight of books and supplies they are carrying as they attend class.
'Kay.
So the variable of interest, would that be, like what they're...
Well, let me ask a question. What are they asking the kids? Are they asking them how much does everything weigh? Or are they asking them, does it weigh too much? Is it just right? Is it too little?
Oh, the weight of the books.
That's all they said. They're being asked about the weight of their books. Okay, so essentially what they're being asked to do is report back how much their stuff weighs.
Right.
Okay, that's the variable, the weight of what they're carrying. Is that fair?
Yeah.
What kind of data is it? Quantitative or qualitative? It's definitely quantitative, isn't it?
Yeah.
And what kind of quantitative, therefore? Definitely, Addie. It's got to be, right? Because it's weight. How do you get a weight? You measure it, Trev. You measure. Put it on a scale and you measure. It's a number for sure. But to get that number, you actually have to weigh it. Suppose instead of asking the weight of the books they're carrying, suppose they were asked how many books they were carrying. Right? Suppose they were asked how many books versus weight. Would that be qualitative or quantitative? It's still quantitative. Because it's still what? It's still numbers, but now it's a countable quantity. Oh, this one's got 5 books, this one's got 6 books. You count those. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You don't put them on a scale and weigh them or measure them. Is that fair? Now, can you see why the number of books in a backpack might not be as good an indicator? I'm imagining that the reason they're doing this study, the same thing happened at my high school that I was teaching at about 15 years ago. They were concerned kids were carrying too much crap around. They were hurting their lower backs in their formative years. Why would weighing the books be a better indicator than telling you how many books they're carrying with them? Or better yet, why would weighing what's in their bags or what they're carrying be better than talking about how many things they're carrying from class to class? Why do you think? Rachel, go ahead.
Because the books, they're different sizes, they're different weights.
They can vary, can't
One
they?
could be carrying a paperback and a notebook and 5 pencils, and some other person could
That's
be
like
carrying
12 things.
like an iPad, 5 books, a binder, specific things.
That's like 18 things I lost track. But yeah, exactly, right? I mean, if you're carrying a deck of cards, I have 52 things with me right now. I mean, you have to define what a thing is at that point. It's much easier to put the whole thing on a scale and say, oh, it's 28 pounds. AJ, go.
So if it asks you to list a few values that might occur in the sample,
Go for
do
it.
you mean like the pounds of the book?
Exactly. So what would a kid say? What would a kid say at a school that says, okay, how heavy's in your bag? I mean, what do you think?
20 pounds.
20 pounds. I think that's probably fair. I mean, an Nalgene, water's 8 pounds a gallon. So think about that. A quart and a half of water is 3 pounds of weight. So compare that to a backpack. Kind of think of it that way. So yeah, 20 pounds I think would be feasible. 10 pounds, 15 pounds, 25 pounds. Would it be cool? It'd be cool to see the distribution of all those weights on a graph. I actually asked for that because a study was done at my old high school, as I said, and they outlawed backpacks after the study because their claim was that the books were too heavy for kids to be carrying around. They were worried about physical problems. And I was like, that's totally cool. Can I see your data? Never got it. Asked for 5 years, never got it. So, interesting. I'd love to see it, but I never actually got the data. And unfortunately, I know the kids were never asked how much their packs weighed back in the day. They were asked things like how many books, the size of your backpack. One kid I remember used to carry a backpack around. He put everything, clothes, gym clothes, sneakers, every book he owned, God only knows what else, his family pets, in this bag. And you could see him come down the hall because all you saw was this backpack, no head, a couple feet, and occasionally the elbows sticking out to the side. So, I mean, obviously you see that, you're like, oh my God, kids carry too much weight. Well, that kid does. But is he representative of the entire population of the school? Maybe not.
So
But
what type of variable would be books and supplies? Is that?
well, the type, I'm thinking they're asking for qualitative versus quantitative.
Oh.
And based on the fact that they asked for how much it weighs, Haley, I'm calling that quantitative,
Right.
continuously quantitative.
Okay.
Because you're going to measure that. And you got to be careful, too, because if you ask somebody, I used to do this in 244, I might start doing it again. If you ask somebody to report their height and then measure their height, and or report their weight and then measure their weight, sometimes you get discrepancy. So if you ask somebody how heavy is your bag, it's better to take the bag and weigh it and get the number that way rather than asking somebody how much you think is in the bag. Because we're horrible. I mean, personally, I am horrible at estimating how much things weigh. Part of that's being a dad and carrying a 5.5-year-old all the time. Just do it. He's 45 pounds. So I weigh 40, whatever he told me he weighed. I weigh 45 pounds now. Down, get on my back. Let's go. I'm fusing my vertebra. Whatever. Doesn't matter.
But that's exactly what I was thinking about. I
Uh-huh.
was not thinking about actually measuring, but asking.
You-
Because
exactly.
and that's what I thought qualitative, because I thought they will say too heavy or too.
Oh, well,
not
that's,
heavy.
but so that's why I asked, what exactly are they asking for? It sounds like they're actually asking for the weights.
For the weight.
Not if, and that's why I asked too, because is it too heavy? Is it just right? Is it too light? That's qualitative.
Yeah.
That's an opinion almost. It's a sliding scale Likert score.
And as for example, mistakes might, the book says fractional value might occur when we measure the weight. That's what it's from the book. So
Fractional
fractional
values.
value, I don't know.
I would hope it would, actually.
Yes, it might occur. Yes, fractional value might occur when we measure the weight. That's exactly from the book. And I
Are
want
they
to
saying
tell-
that's a possible error? Or
Yes,
that,
yes, exactly.
I
So
don't see how that would, I
know,
don't see how
that's-
that would be an error, because if you're putting something on a scale,
I wanted to ask you this question because I
I don't
know
get
what it means.
that.
Okay, it's page 10.
Fractional error.
Fractional value. Something. Yeah. For example, the variable weight of books and supplies you're carrying as you attend class today is an example of a continuous random variable. The values of the variable may be found by measuring the weight. When we measure, any fractional value can occur. Thus, every value along the number or line is possible. I mean,
Yeah, that's what continuous means.
yeah.
What is the next number bigger than 1 pound? It's a trick question.
Yes.
It's a trick question.
Yes.
There is no next bigger. It's infinitely close to 1. Now, the next discrete value up from 1 is basically 2. 1 book, 2 books.
Yeah.
Right? But then the next continuous value up from 1 is infinitely close. So that's what they're talking about, fractional. Actually, a better word would be irrational. Fractional or unfractional, but decimal between 1 and 2. I would hope that they would occur. I would hope those would occur. Because depending on the precision of the instrument you're using to measure them, you should get that kind of stuff.
I thought the scale might be wrong and it can be different.
Well, no, the scale not so much wrong, but imprecise. If the scale only measures to the nearest whole pound or the nearest half pound, that's the precision you're stuck with. I mean, you're stuck with half-pound increments. That doesn't mean the data is still not continuous. It just means that you're relegated to those jumps.
And in regards, for example, to the qualitative, it's really difficult to say because for a man it can be not heavy at all. For example, if you ask a woman.
If they did this qualitatively, I would throw the whole thing out.
Okay.
Honestly, I would throw the entire
Yes.
study out because you're asking people's opinions.
Uh-huh.
And I shouldn't say that. It might just be a survey that's done to stick in the sidebar of some magazine just to occupy space. In which case, I guess it did what it's supposed to do. If you're trying to do like research or create like a rigorous result based on it, I would throw it out in a heartbeat. And that's what you have to look for too. Well, we'll close this up and then we'll have you kick you guys out to take 5. But always check the variable, how it was defined and how it was measured. Anytime you read any kind of report online in the news, check the variable and see how it was measured. If it was done by self-selected or free response in a non-metric way, it's suspect, immediately suspect. It's immediately suspect. So always check it to see. Cool, let's take 5. Let's get some air and some water. Yes, get some air and some water. Let me shut this bad boy down. We record? We are. Gesundheit, yes, indeed. So what I want to start talking about now is, that's framed up pretty good, ish. Whoa. I may have to stick something on that leg. What I want to start talking about now is how to quantifiably measure this wonderful data that I think we have a much better grasp on. Oh, did we get the battery going? Yes. So take a look at this. While you're taking a look at that, I want you to form an opinion about that. Then we're going to analyze it, because that's what we're going to do it here. Some of this, while you guys are analyzing that. Don't eat these yet.
Okay.
There's a point to this.
All right.
There's a point to this. What do you think about, these are 3 different commercials that Walmart used. I think it was 07, this was in 06, and I want to say that was 08, but I'm not entirely sure. What does Walmart mean when they say independent research from Global Insight has shown Walmart saves the average American family $3,100 or $2,800 or $2,500, depending on the year they're publishing it, no matter where they shop. What do you think, AJ?
Comparatively to maybe shopping at another store like a Fred Meyer or Safeway.
That's the first thing I thought of too, until I read the no matter where they shop bit.
That's what I thought.
So somehow, yeah, just real quick so I get a count to make sure I didn't. How many folks did I put lollipops in front of? Just raise your hand, just so I get a count. Perfect. Awesome. Dakota, you're number 10. I'm going to need you for a second, too. Just not right now. You don't need lollipops, but I'm even number 10 person. Just because it's easier to divide by 10 than 9. So, yeah, no matter where they shop. So, it's interesting, isn't it?
Does that mean they would be saving, like on average, maybe they like totaled all the savings from everyone who shopped there compared to another store? And I don't know, it just doesn't make sense. And so maybe like, even if they don't shop there, they would have saved, but that doesn't make sense.
No, actually, that economically, from what I understand, it doesn't make sense. Tell me your name one more time.
Jada.
Jada, thank you. It didn't make sense to me until I had an economist explain it to me.
Okay.
Does anybody know what claim is being made here? And I'm not doubting the veracity of it. I'm doubting kind of the way it's said. What do you think, David?
Well, there's 2 ways. First of all, it doesn't make sense just to read it, but the only way you can shop it, the only way you can save money without shopping at Walmart is if it forces the competition to lower the prices.
And that's what they explained to me. That's what my economist friend explained to me. That just Walmart being in a neighborhood, in an area, forces prices down because they're able to operate at large scale. This is how Costco works, for that matter, right? This is why you buy a humongous box of granola at Costco, and suppose it costs 10 pounds, and you buy 10 1-pound boxes of granola, and it's going to cost more to buy 10 individual 1 pounds than one big 10-pound box, due to packaging, due to shipping, all kinds of micro reasons that Walmart has down to a science. So, very, very interesting, and I think that's the claim no matter where they shop. However, I always encourage folks to take a look at the data behind this, because that came through very quickly on the, and then I'll have this posted for you later. Please don't write all this down, or don't even try to write all this down. So what I did was I went and I found Global Insight's report from the 06, actually it was the 07 report, it was through 06. So this is beautiful. Walmart is likely to have a significant impact. Sophisticated logistics, total factor productivity, lowering its overall cost structure, suppliers to offer significant volume discounts. Walmart has in turn passed along to its consumers. David, exactly what you just said. Because they're able to operate so efficiently at such a large scale, they're able to charge you a few lower prices at the register, which means overall the same product on average, according to this, is going to be cheaper at Walmart than some other store, which makes the other stores have to lower their prices to be competitive, which makes you save money even if you don't shop at Walmart. Interesting? Interesting. Very interesting. Very interesting. So interesting. Their objective, Global Insight, is to determine if Walmart's presence has had an impact on measured consumer prices. Now, I bolded this because I thought it was interesting. The CPI, which is what they're comparing it to, the Consumer Price Index, that's what they're using as a metric for measurement. Durable goods, non-durable goods, and services. So durable goods and non-durable goods are what they sell. Services are other stuff that's not sold. Durable goods and non-durable goods are 40% and 60%. If Walmart has an impact on prices, it would have to be in those first two. Because that's essentially, if you will, what they're providing to the public. The services are part of the cost structure, cost of electricity, cost of rent, things like that. But that's not getting given, if you will, to the consumer. It might be reflected in the prices, but it's not being sold to the consumer. So I went ahead and took a look at some stuff. This is the inflation, the CPI, if you will, based on those two things, durable goods, non-durable goods, or commodities, what they call them, and services. Now, please notice, this is in a number of urban areas. You got San Diego, Boston, Portland, I think is the closest we get to Bend, okay, which is not surprising. When they're looking at 85 to 06, ranked by MSA. What was MSA? I think it's just overall. It's just decreasing as it goes. Notice the largest piece of each of those bars is contributions from services, not from sales. So when you look at the overriding effect of the CPI, it's not due to what's being sold. It's due to other things that are outside of Walmart's control affecting the prices. You see with me so far? So CPI is what Global Insight is using as a metric to measure savings. Okay, what they're using as a metric to measure savings, but that metric is by and large in every single metro area, mostly service driven, not commodity driven. Is that fair? Is that fair? That concerns me a little bit. It concerns me. Actually, I shouldn't say that. That doesn't concern me. What concerns me is that Walmart puts an ad out saying, we're going to save you $2,300 no matter where you shop. Well, maybe the economy is saving you $2,300 no matter where you shop, but Walmart's taking credit for it. That's got me a little bit concerned. Smidge concerned. Here's something else that makes me a little bit concerned too. This is a scatterplot, if you will, a correlation between, again, CPI change and Walmart square footage. Now, each of those dots, even though San Diego spelled wrong, each of those dots represents a town. There's Alaska, here's Boston, here's San Diego. What they're trying to show is a relationship between the growth in the consumer price index and the change in the square foot per capita in Walmart. So in other words, as the CPI decreases, the Walmart square footage increases. And they put a very helpful little best fit line in there, more to follow in 244. The problem is that this doesn't prove anything. It doesn't prove anything because correlation, if you might remember from a week ago, does not imply what? Remember the word that goes after that? You might not. It's only been causation. Just because this is happening does not mean Walmart is causing it. It's just happening. It's like if you look historically at the number, I think I may have mentioned this in class, the number of cases of Cuban rum imported into the United States from 1650 to 1850, and the number of Methodist ministers in the United States from 1650 to 1850, it's almost a perfect linear relationship. So obviously the Methodist ministers are bringing their own United States. No, that's a ridiculous example. This is a less ridiculous, less obvious example. But just because something is showing a correlation, albeit weak one, does not mean that Walmart is causing anything. Is that fair? And what's interesting is Global Insight itself. Look at this. This is one of the last sentences in the report. Go ahead, take a look at that. The report admits that the three largest chunks of what's causing the CPI change are outside of Walmart's control. Cost of electricity, unemployment rate, although Walmart might argue they control unemployment rate in a lot of ways because they hire so many people. High wage industry employment share. All of this has nothing to do with what Walmart is controlling. They're controlling the other, if you will, 11%. But yet it made its way into a commercial. And what's interesting is nobody bothers to challenge it. So there it is in a commercial. If they're right to put the commercial out, it's your obligation to go find this out and be like, wait a minute, might it be something else? Correlation doesn't always imply causation. Just because the prices fell doesn't mean you caused it. Doesn't mean you caused it. But all of that is wonderful. But the biggest concern I have is what the hell is the average American family? That's what I want to go back to. Right back to that. What I just did right there was like a stat of the day fact check with you and for you. What the hell is the average American family? What the hell does that even mean? So, the word I want to analyze right now is average. And the topic I want to talk about, I want to blank this for a second. The topic I want to start talking about right now if I put the screen up. It's got a break on it, which oh, look at that. Oh, that's fancy. Yes, and yeah, okay. All right. It's got a governor, like my old rental van. I want to talk, now that we kind of understand data and how to be critical of it, which is fantastic, I want to talk now about measures of center. Only because this is such a prevalent part of what you're exposed to on a daily basis. There's another parallel topic that goes along with measures of center called measures of spread or measures of dispersion or measures of variation, which we'll get to probably starting on Wednesday. But what I'm talking about now is measures of center, and this is tied back to the example I just erased. 33.2% of those in the sample had allergies. 33. That's the center of the sample. It's basically on average what's going to happen over those 1,200. Now the measures of center are basically ways to describe a typical member of a data set. That is not a very good definition, but I've discovered that there really isn't a very good, if you will, dictionary definition of measures of central, also called central tendency. What I've discovered is it's much better to talk about the measures that we can have and then deal with them. So the first one I want to talk about, there are three that I want to chit-chat about in class. There are three that I want to chit-chat about in class. There are many more than three. Many more than three, at least a dozen that I know of. But the three that we're going to talk about in class I think are the most important. What I need, though, is I need everyone that I gave lollipops to grab that fistful of lollipops and come on up here and stand in a row in front of the board. Dakota, you two, you're number 10. And I'm going to pull this back so we can see you guys. Come on up. Yeah, go ahead and hold them up, maybe like a little bouquet, so we can see how many you've got. All right, good. Yes, and when we're done, we can, of course, spread them around and share them. That's absolutely wonderful. Get this cord out of the way so nobody gets tripped other than me. All right. You guys cool with being on camera? You look lovely. You look lovely. Look at that. So we got beautiful. Okay, so we're going to play the home game as well. Hold on nice and high so we can see what you got. Dakota, hold up your empty fists. Very, very good. Very, very good. All right, what I would like to know is, on average, how many lollipops does each member of that group have? And you're not allowed to do the average like you've done it since you were teeny tiny. Because I know the first thing you're going to do, as soon as I said, find the average number of lollipops per person, what's the first thing you're going to do? You're going to start counting up how many there are. And you're going to add, you already did. Robin's already got it done. So you're going to add them all up and divide by, that's why I put the code up there, make it 10. So on average, how many lollipops are there? But you're not allowed to use that little formula by summing and then dividing. I'm not saying forever you won't be allowed to use them. But you, right now, in order to understand why that formula works, because that's the problem is, I think we use that formula blindly without knowing how it works. Hopefully after this experiment you'll understand why. So how can we figure out, what do you guys think at the front or at the desks, how can we figure out how many lollipops on average these folks have without adding up and then dividing by 10? What do you think? Give me some ideas. What do you think? What do you think? What do you think, Elena?
I think it's 3.
You think it's 3? Why do you think it's 3?
Because some of us have got more, some of us have less.
So what Elena's doing, I love this. She's kind of thinking like a balance, which is actually a great way. It's a fantastic way of kind of analyzing. Let's draw a picture, if you will. Okay? How many lollipops do folks have? Let's make a quick little dot plot. Trev, you got 2. Anybody have? Dakota has none. Anybody have 1? We got 1. We got 2. 3. Who's got the most?
9.
David, how many do you have?
9.
You got 9. 4, 5, 6, 7, 8, 9. Okay, let's do a quick little check-in. Dakota has none. Who has 1 again? Jada and Haley. So that's 2 1s. Who has 2? And that's Jen. No, Jen has 3. So you got AJ and Trev. There's 2. 3. That's going to be you, Jen. Okay. 4. We got 4, we got 1, that's Elena and Liz, thank you. So we got 2 4s. 5, anybody got 5? Nobody's got 5? 6, 7, 8, and David's got 9. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Who didn't I count?
I don't think you counted me. I have 4.
Oh, you've got 4. Perfect. And there we go, Rachel. So there's our 10. There's our 10. So remember, we're not allowed to add up. But Elena made a claim that she thinks the average is 3. Now, looking at that graph, Elena, I don't know if you can see it where you're standing over there. Looking at that graph, where would you have to put your finger to balance it? What do you guys think? Trev, could you use your finger? Just put your finger and point up. If this was a balance, a fulcrum of the balance, can you point your finger up like this? Start at 0 and slide to the right. You guys tell Trev where he needs to stop.
2.5.
2.5? Got to vote 2.5? I like that, Jordan. Other votes? Elena voted for 3. AJ staying further than 3.
Oh, yeah, I agree there.
So like 3.5? You think like 3.2 somewhere in there, AJ? Somewhere in that ballpark? So it looks like we're kind of voting for 2.5 to 3.5. What are you thinking, Robin?
I'm thinking like right in the middle of 3.
Right in 3. Just thinking 3. Why are you so certain it is 3? I like that. I like that certainty.
Because I'm trying to distribute it on each side and then just...
Oh my goodness.
I think
She's what are you doing by distributing it, Robin? What are you doing?
I am taking the dots and moving them. Like,
And what does that really do if you take the dots and move them? So in other words, you kind of feel bad for Dakota, standing there with no lollipops. So why don't we give Dakota some lollipops? I'm looking at you, David. You with 18,000 lollipops. Why don't we give, how many should we give Dakota? What do you think for starters, David?
3.
at least.
Give him 3? At least 3?
Yes.
Give him 4. Give Dakota 4 if you don't mind, David. That leaves you with 5, doesn't it? Or give him 5.
I gave him 5.
You gave him 5. So now Dakota has 5. David's got 4. This is what Robin is telling us to do, and I kind of like the idea. What are you thinking, Haley? What are you looking at? What are you looking at?
She needs 1 dot.
You look at the dot. You have 1.
Yeah.
So Haley's got 1. Do you think she should give that 1 to somebody, or maybe take a few from?
I should keep this one.
You should keep that one, and maybe even
Get another one.
get a few more. Maybe I picked on David last time. Who wants to donate? There we go. We got an extra one from there. So by doing this, if we do this and keep doing this and keep doing this, what's going to happen eventually, friends?
It's gonna eventually even out.
Do it right now. Make it happen. Robin, see what you created? Beautiful, my friend. Make it happen, friends.
3.
We got 3.
Make it happen, friends. Everybody now has
3.
which means the average number of lollipops per person is 3. You just demonstrated why the formula works, didn't you? Think about it. I said you couldn't use the formula. But this is why the formula works. Because when you add them all up, which you would have added to 30, there were 30 lots, so I had to pay. I was at my floor in my office counting these out, and I got them twice. I'm like, no, go away, I'll come back. I want to make sure it was exactly 30, because I wanted them to divide nicely. When you add everything up, you forget that Dakota had none, and David had 9, and Jada had 1. You forget all that, and you say, here's the pot of 30 lollipops. Then dividing it by 10 distributes the exact same number to each individual person. Fantastic. Thank you, friends, proving the point. And if you want to spread the sugar around, everybody else in the room, yes, I think a round of applause is in there. I think so. Fantastic. We're throwing lollipops. That's good. That's good. Thank you for being such good sports with the camera, too. I appreciate that. Oh, I'm sorry. Go ahead, Haley. Yeah, everybody got some sugar? Yes, get some sugar.
Anybody want 2?
Anybody want 2? AJ wants 0. You don't want any? If you don't want them to make a pile on the front, we'll recycle them into the next glass. And then we'll get rid of them somehow. There we go. So, what you just discovered, perfectly, get this back to the front here, is the first measure of center, which is the average. So the first measure is the average, sometimes also called the mean. Now, there are more than one kind of average. There's an arithmetic mean, which is essentially the one we're talking about right now. There's a geometric mean, there's a harmonic mean. All of these have wonderful, wonderful applications, but the one that applies to most of our lives on a fairly regular basis is the arithmetic mean. And the way you find the arithmetic mean, forget it, we'll just call it the average, or the mean, is you sum up I have no problem with you using this formula. I have no problem with you using it now that you understand why it works. You sum up all the data values and you divide by the number of data values. And I know we all knew that formula coming in here, but unfortunately, what we don't know necessarily coming in here is why it works. So what's the big idea of an average once you sum them all up and divide by how many there are? What are you really trying to establish for the entire data set? Go ahead. What does this mean? You got it, Elena.
I don't know,
love
like
this.
this kind of scale.
Such that each member of the data
It's
set...
got the same amount.
Exactly. I like to think of this in there's a couple different words I like to think.
Sharing.
I love the word sharing. I see that's one of the words I think of when I think of average is sharing. Go ahead, Robin. Good. Dividing equitable divisions. Yes. So there's all kinds of words I like to establish with this. Equitable division. I hope you don't mind if I put the word equitable in there, Robin. Equitable division.
That word.
Equitable. Well, me too. Equitable division. Sharing is another great word to use. I'm kind of a fan of word association, especially with central tendency, because of the three different things I want to talk about today. The three different things I want to talk about today are all talking about a typical member of a data set. But sometimes a typical measure in one might not be the best typical measure for another. So sharing, I also like the word balance. I like thinking of it as balance. That's why I love this dot plot up here, right, the scale. So when I had Trev kind of putting the fulcrum of the scale, it might seem kind of weird that you have to put the fulcrum right here at 3 to balance. Until you realize David was way out there. David was way out there. But when he took his 9 and donated some of his 9 to Dakota, who was at 0, that 0 went away, didn't it? And a 5 dropped in where it was, and this 4 went in there. So the 9 was gone, the 5 became, the 4 became, and the 0 was gone, which means we're getting closer to that center. Now that is a different data set at that point by doing that. That's not as extreme as this one was. That's a more extreme data set. And I'm not saying that an average would have been necessarily the best measure of center to use, but more on that on Wednesday as well. But that's what the actual average would be. Fair enough? So that's the first. Now what I want to do now is I want to revisit this and the other two, but rather than using the lollipops again, because now you've distributed them out and then we're enjoying them, which is totally great, let's use your key data. Let's use your key data from last class. I've got it collated up here, friends. I've got it collated up here. Whoa, jeez. It's got a break going both ways. So let's shut this down temporarily. Oh, you can't see that. There we go. Here are the number of keys you guys had with you. Let me make it a little bit smaller so you can see it. Here's the number of keys you guys had with you in class on Wednesday. Let me get this recentered. This is going to be hard for those playing the home game to check out, so I'll read them off to you. And you probably want to take these data down. We'll play with these data today quite a bit. We'll probably play with them into Wednesday as well. It's a bit superfluous. It's silly data. Number of keys with you, but it's cheap data. It's easy for us to get really quickly. And I don't want to focus so much on the getting of the data or the type of data as much as I want to focus on what to do with the data. And right now there's 3 things I want to do with it. So 2 of you had 1 key. Somebody had 2. 4 of you had 3 keys. 3 of you had 4 keys. 2 5s, a 6, an 8, an 11, a 12, and a 17. 11 to 12 and a 17. So I'm going to make a little side chart. Maybe I'll do it over here. So for our key data, and I want to talk about the 3 different measures of center with regards to our key data. So the first one is we talk about the mean, the average. There's a symbol that's often used for a sample average. So I'm going to call this a sample, not a population. I'm going to call this a sample average, which means I'm making it a statistic. Make peace with this right now. I could make this a population average if you guys were my entire population that I cared about. And sometimes you are. Sometimes you are. Like when I grade your exams, when I grade your projects. I mean, you're basically my population. This class is my population. But right now, I want you to get used to the idea of a sample and a sample average. So I'm going to call that x with a bar over it. X with a bar over it. That's called x bar. X bar. Okay. And x bar, I should probably put this over here. This might be a little more helpful. There we go. It'll maybe helpful if you can see it at all. X bar. And x bar, rather than, there's a couple symbols I like to use. I'm not a huge fan of overdoing formulas in this class, but there are a couple symbols that I think are pretty helpful. One of them is the big sigma notation. Whenever you see a big sigma notation, it means you're going to be adding stuff up. So that means add a bunch of stuff up. And when you stick a little x next to it like that, that means add up all your data. So essentially what this means is add up all your data values. So in other words, it's a symbolic version of what the numerator of that fraction over there has described to you. Sum up all your data values. That's the same thing. Sum up all your data values. And then you divide. We're going to call it lowercase n for a sample size. This is the number of data values. This is the number of data values. So this is a shortcut. I love this big sigma notation. We're going to use it quite a bit in here whenever we're talking about new ideas. Adding is one of those things that happens all the time in this class. You're constantly adding things. You're also constantly subtracting, you're constantly squaring, you're constantly square rooting, and we'll deal with all of that in turn. Right now, let's worry about adding, about the addition. Cool? So, what is our average number of keys? Anybody add them all up? I'm going to cheat. That's okay with you guys.
Average.
I'm going to add equals, so, there we go.
Just don't come.
I get 92. Anybody go ahead and add those up already? Didn't wait for me to do it? That's cool too. So for us, I get 92 total keys. I get 92 total keys for, I get 17, is that 17? Ah, yes, somebody's saying 16. This is a great little combinatorics problem. It goes from cell 19 back to cell 3, which is 16 different, but you have to count cell 3, which is goofy, the little +1 thing. We'll deal with that on Wednesday as well. So I get 92 keys distributed to 17 people. Let's get a decimal of accuracy here. Equals that divided by 17. I'm getting about 5.4 keys.
Yeah, I was close.
5.4 keys per person. I'm kind of a unit fan, even though I'm out of board. So I get an average, a sample average of 5.4 keys per person. So in other words, the lights just go off, that's okay, I guess. Hello. In other words, if I made all 17 of you stand up here with your keys and do what we just did with the lollipops, you'd have to give everybody 5.4 of them in order to spread them out evenly. Which means we have to have a set of metal snips up here at some point, snipping as we go, snipping as we go. Is that fair? Is that, well, not the metal snip part, that wouldn't be too fair, because it would bring back into your house or your car. But that's the idea. In order for us to have a sum total of 92 keys, distributed evenly, or equitably divided, or balanced between 17 people, you'd have to have, or shared between 17 people, you'd have to have 5.4 keys per. Does that make sense? Good. That's what an average is. I mean, I know we very often just add and divide, but there's a reason why we add and divide. The formula is set up to be equitable, to be sharing, and to be balancing. So if we were to make a dot plot like this with our keys on it, we'd have to balance it right about 5.4. Right at about 5.4. We'll also see a graph of that later. I got it later on in the Excel sheet. Sorry, it's coming. It's coming. I was 3 steps ahead of where I needed to be, and then I got stuck on a loop. Cool. Okay, that's good. I wonder if this is visible with the light off. Is the light off okay? Maybe the room knows something we don't. Like this weird, strange thing here. So that's one of 3 measures of center. That's one of 3. And it's a very, very, how many of you have heard of an average before? Yes. I mean, even before we talked about it in class with Inigo Montoya and the Princess Bride. Yes, of course. So that's one, the mean or the arithmetic average. And that's how you calculate it. So for our key data. Another one that's fairly popular, and with good reason, is called the median. The median. We'll go ahead and number these two. 1, 2. Some of you nodded and said, "Oh yes, median. I remember median. You've heard of median before." Tell me what you remember about medians of data sets. We're still talking about typical data set values. Haley, what do you remember?
Isn't it from least to greatest and then the number in between?
Good.
Or in the very middle.
Good. So basically, the first thing you do with the median, we'll call this number 2, is you want to arrange your data in order. Okay? Arrange your data in order and find the geographic, I like to call it the geographic middle. Find the geographic middle of the data set arranged in order. That's your median. That's your median. So let's take a look at our data set, and then I want to come back here and I want to compare the median to the average. But anybody want to say anything else about the median? I love that. A big key is making sure that it's in order. You got to make sure that you shuffle them least or greatest to least to greatest or greatest to least. Either one's totally fine. Tell me, Jen, go.
In some cases, don't you use an average to find the median? Like if you have an even number,
You'd have to, wouldn't you?
find the
You'd
average.
have to. Well, we'll chit chat. I know we have an odd number up here, but we can take one out and talk about that. Exactly. And there are formulas for medians. I mean, I've seen them before. There's all kinds of neat little formulas. Don't worry about it. Don't worry about it. Technology's going to help us. For right now, I want you doing stuff manually. So let's grab that's shorter than I think it is. Let's grab our raw data. Here it is. Okay. So we got 1, 1, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5, 8, 8, 11, and so forth and so on. What would the median of this data set be? As a matter of fact, let me do this. This might actually help us if... No, if it was pointing somewhere else and I wasn't writing right here, it would help us. Well, maybe it will. Let me use a different color. So where's the middle? Where's the middle? I have a vote of 4. How'd you find 4 so quickly? Was that you, Haley? Go ahead, because you're jacked up on sugar. That's good.
Yeah.
How'd you find 4 so quickly? What'd you do?
I went like this.
Good. So what Haley did, so what I was going to do with my orange marker here, she said, okay, the smallest one is 1. The largest one is 17. Cross those off. The next biggest is 1, then 12. So I'm crossing them off in pairs. So 2 crossed with 11, 3 crossed with 8, 3 crossed with 6, and so forth. 3 crossed with 5, 3 crossed with 5, 4 crossed with 4, and I've got 1 left, which means my median is 4. My median is 4 number of keys. The typical student in this class has a median of 4 keys per. 4 keys per student on median. Notice it's different than the average. It's a little smaller than the average. We'll talk more about why momentarily. Go ahead, Elena.
For example, the first starts with number 3, right? I like the first 3, then 19.
Yeah,
Actually, you can do 19 minus 3 is actually
16.
16, so divide by 8. No,
Divide by 2 gives you 8.
Yeah.
No, what Elena's coming up with, there is a slick formula, a computational formula. You can figure out how far you have to come. If there are 17 data points. So this goes back to what Jen said also. If you have an even number versus an odd number of data points. If you have an even number, so for example, if I put my number of keys on there, which was something like 22 or something that day, if you put mine on there, then we're going to end up getting down to 2 4s in the middle.
Yes.
Not 1. Well, then, once you get to that point, you just take the average of those 2. You go, what's between those 2? You just create a data point, if you will, for that. You can figure out a mathematical reason for but don't sweat yourself on that. In this case, take the 1 away, divide the remainder by 2, and come in that far.
Yeah,
So drop the lowest 8. The 9th is going to be your data point. I mean, that's wonderful, and that's what technology does to get us these values. But it's not worth. I'd much rather you keep the idea of the average formula and not worry about confounding it with the median formula too. Cool so far? So, how is the actual let me turn the screen off here. How is the actual computation of the median versus the computation of the mean. We're getting different results, 4 keys versus 5.4 keys. Why? What is not being accounted for in the median that was being accounted for in the average? And this is a bit of a tricky question. You might not catch it right away. There's something that is not being accounted for in the median that definitely is being accounted for in the average. Go ahead, Jordan.
Actual value?
Good. So let me ask you a question. Let me put this back on again. Suppose, for example, who had 17 keys on awesome, Addie. Suppose you had 170 keys versus 17. So in other words, this number is now 170, not 17. Would that change the median at all? Not at all. You'd cross off that 17 and you'd cross off the 1 up there. And they'd be gone. 17, 170, 1,700. Now, if Addie had 170 keys with her on Wednesday, would it change the average? Hell yeah, it would. Because this number would no longer be 92, it would be 150, whatever, 153 more than that, which would drive the average. You got to be careful when using averages if you know your data has those kinds of outlier values. Very often, when talking about things like house prices, they don't use average house prices, they use median house prices. And the reason is, why? Why would they use a median house price versus an average house price? Why do you think?
Probably looks better.
Why? When you say looks better, define better. I love that, Haley.
Better. It'd be cheaper, maybe? I don't know.
So I love what you're saying. What are you thinking? So you're envisioning a neighborhood, I'm assuming. Mm-hmm. I'm envisioning my neighborhood about 5 years ago, right before everything kind of collapsed. We live on the northeast side of town, pretty affordable. Guy came in, borrowed $500,000, put $250,000 of his own money in, and started building what essentially is an Aubrey Glen house at the corner of my street and the next street over. And I'm thinking, what the hell is this guy doing? And my neighbors are like, this is great. The average house value of our neighborhood just went up. I'm like, well, yeah, until things exploded, which they did like 3 weeks later. And the average house price did go up because essentially that was like Addie trading in her 17 keys and bringing 170 keys. We put less than $200,000 into our house when we built it. This guy puts $750,000. Well, yeah, the average house value is going up, but the sale prices didn't change at all because he never sold the damn thing. He lost all the money he had before he had a chance to sell it. So that wouldn't be, in my opinion, a fair representation of the value of the houses in my neighborhood because you got a bunch of houses that are all worth about the same and this one whopper that comes in. So that's why the median is often used for real estate prices because it's more fair, if you will. Go ahead, Haley.
Because you have the biggest one on the bottom, so you're going to,
It's going to cross off with the smallest one on the bottom. Now, I love what you said when you said it makes it look better. I got into a discussion with a real estate appraiser about 4 years ago who started using average house prices versus median house prices. And I said, you shouldn't do that, and here's why. He's like, I know. But the average tends to inflate with respect to real estate. And he was trying to paint a rosier picture that was actually, and I couldn't fault him for that. I'm like, that's actually that's a fair thing to try to be doing, misleading though it might be. So that's where the median and the average kind of diverge, if you will. Cool so far? All right. Now this is the most computational. This is the next least computational, I guess. And the third that I want to mention and not talk a whole lot about, except for when it's useful, and it is useful more often than it is actually used, is the third, which is called mode. The mode of a set of data. And all that is the data point that shows up the most frequently occurring. That's all. Occurring as 1 R, 2 R's. 2 R's. Looks like it should have 2. Thank you. It's the least computational. Because basically, unless you're using Excel, you have to kind of just inspect the data set to see which one shows up the most. I got 3 showing up the most, although I do see 4. It's a very small data set, which means there's all kinds of fun quirks that happen. We're going to call it 3, just because that one does show up the most. So our mode is going to be 3 keys per student. 3 keys per student. Now, you can have multimodal data sets. For example, you can have a data set that has two modes. Sometimes it's called bimodal. I would actually almost argue this is a bimodal data set because the 4 and the 3 is very close. But let's create, I mentioned to Elena about an hour ago or so that there are certain things that are black and white in this class. There are certain things that are shades of gray. Let's make mode black and white by simply saying whatever data point shows up the most, that is the mode. Let's leave it at that. So the mode for this one is going to be 3 keys per student. The reason the mode doesn't get used enough, in my opinion, and this goes back to one of the homework questions you guys asked about, the mode should be used. It should be used when you have qualitative data. You should not be averaging Likert scale scores. And in my opinion, you shouldn't even be medianing them. Because medianing them, although a median I can live with, I definitely can't live with an average. I mean, I can live with 5.4 keys on average. I can live with that, even though it doesn't make a whole lot of sense to have 0.4 of a key. Back in the day, at the 1990 census, there were 2.5 kids per average per American family. Okay, 2.5 kids, which sounds terrible, except until you realize that's 25 kids per 10 families, which makes perfect sense. 3, 2, 3, 2, 3, 2, 4, 1, 5, 0, and it averages out. It averages out to 2.5 per. I have a big problem when you start averaging, say, Likert scale data. You can't average a strongly agree and a strongly disagree and call it neutral. There's an old phrase, you stick your head in the oven and your feet in the fridge, on average you feel fine. No, no, but that's essentially what you're doing with Likert scale data. Cross off this one and this one and call it 0. That implies that that scale actually has a metric between it, which it doesn't have. It's a 1, a 2, a 3, a 4, and a 5, and there is nothing in between because it's qualitative data. So basically, modes should be used with qualitative data. That's not saying they can't be used with quantitative data. But when you have qualitative data, really logistically, or legitimately, this is the only one you should be using. You can't average qualitative data. You really can't even median qualitative data. I mean, you can't. You can kind of, I've heard arguments that maybe lean me a little bit towards a slight justification for a median for Likert scale data, for example. Maybe. For example, strongly agree is above agree. Agree is above neutral. Neutral is above slightly disagree, and slightly disagree is above disagree. So if you will, you can kind of put them in order and then cross them off. I can buy that. I can buy that. I definitely can't buy that for that kind of thing. So what I want to talk about is basically different ways of looking at these 3 types of data and when to use each one. That's what we'll talk about a little bit next, and then we'll lead this into into Wednesday's discussion too. Any questions you guys have right now as far as that goes? Fair enough? Fantastic. Let me see. I need this. No, leave that here. Okay, so let me shut this down temporarily. Go back to this. Now, and all that's wonderful. Fire this back up. All of this is great, except those 3 computations, which I think we've all got down now, are based on raw data, being supplied with a laundry list of data points, like I supplied you guys with. Suppose, instead of having the raw data given to you, you have, like we discussed in class last week, you've got this data presented to you. We're going to come back to our keys, I promise. We'll get back to the keys probably until Wednesday. But suppose you have this in front of you right now. Suppose you have this. Men's LDL, bad cholesterol readings. A random sample of how many men? How many can you say? Got 100 men represented up there. 100 men represented. Okay, suppose I wanted to know, on average, what a men's LDL reading was. Assuming that these 100 men are a representative sample of all men that I'm interested in the population. On average, what do you think their LDL is, their LDL reading is?
4.75, 5.25.
I have a vote. AJ's got a vote for 4.75 to 5.25. Anybody else? Let me hear. Anybody else's votes on what the average men's LDL reading is? You think it's this?
No.
Why is it not this?
Too low.
Too low. How come it's too low? When you think of averages, what are you thinking of?
Because some of them have got 6.75.
Okay, so we're going back to lollipops. There's David over there with his 9 lollipops. And here's Dakota over here with his no lollipops. So neither of those is a good indicator of average because they're the extremes. What does average mean again?
Sharing?
Exactly, we're sharing. We want all 100 of these guys to have the exact same LDL level.
Bells.
Exactly. And it doesn't look like a bell shape, doesn't it? So we want all 100 of these guys to have essentially the same LDL level. So where do you think it is? Let's do what I had Trevor do. Here's the balance point. Where should I stop it?
Right here.
Right here. Okay, very, very nice. I agree. This seconds what AJ said. Now, what's the problem with getting the data presented to you this way versus getting the data presented to you in a laundry list of data like we had before?
That's column. It's too
Well,
high.
It's too high.
I mean, not too high, but that's what sometimes, might distract you from the real answer. You're looking
Well, if the
visually.
real answer that I'm looking for is the average LDL level, that is the, if you will, the real answer. That it is on average between 4.75 and 5. As a matter of fact, you can even get easier and just call it 5 if you want to. You just call it 5. 5 is I think it's milligrams per deciliter is the average LDL level. So if all you're looking for is the average, and I'm not implying that that's all we should be looking for. I'm saying if that's all you're looking for, then we're going to go ahead and call it 5. That's okay. What else do you lose in a data distribution like this? Robin, go ahead.
I was saying that it's visually complicated to read like this.
Tell me why.
Because you have numbers going up and then...
Oh, good. So the second dimension.
I'm seeing to... Yeah.
Okay, that's totally cool. So all those numbers going up means is how many fall into that category. So you've got roughly 32 in this category. Roughly, what's this here? That's 27 in this category. Roughly 7 in this category. Nobody in this category. I totally get it. It takes some getting used to.
Yeah, the bar is just complicated.
Okay. So I'd rather have raw data too, honestly. But here's the problem: you very often don't get it. You very often stuck with this versus actually getting the raw data. So, what else is lost? Go ahead, David.
You have to average each column to get.
Essentially, don't you? There's a problem here. We know that there are, for example, 32 guys in this column. But we don't know, of those 32, how many were at 4.75?
Or 5.
How about, or 5, or 5 1/4, 5.25. You sacrifice that. And I don't have the time, unfortunately, we're going to have to call it here for today. We're going to deal with that in key form, beginning of next time. And then we'll get back into these and we'll see how to deal, because you have to deal with this. This is how most of the data you get presented to you in your journals, in your publications, come at you, just like this. So we have to make peace with this and be able to deal with this. We'll deal with it next time, though.
Sean, can I